So to understand how a tokamak works, you really need to start with the basics of electrodynamics, and that starts with the right hand rule. Now, this is actually my left hand, but TikTok will flip it so it will look like my right hand, so it will work. And what you do is you visualize that your fingers are a magnetic field, your thumb is the direction of the hydrogen nuclei, so that could be a deuteron or a triton or just a proton, but your thumb is the direction of motion of the hydrogen nuclei, and then your palm is the direction the force of the magnetic field will place on that moving hydrogen nuclei. So if I have a magnetic field that's going around the central ring of a donut, which is the tokamak, a really strong magnetic field, and that magnetic field sees a proton moving perpendicular to it, it's going to push that proton. Now that proton has momentum. It's going to want to keep going in the same direction. So when it's pushed down in the direction it's going to cause it to turn. So now it's trying to go a new direction and it's pushed again, and it's trying to go a new direction and it's pushed again, and it's trying to go a new direction and it's pushed again. And it causes it to do this cyclic rotation as it's traveling along that magnetic field. And the reason why that's so important is that that's what keeps it from touching the inner shell of the tokamak. And why you don't want it to touch the inner shell of the tokamak is that these protons and deuterons and tritons are at such a high energy, they're moving so fast that if they touched that inner shell of the tokamak, they would volatilize it, they would vaporize it, and then all of that material from the structural inner shell of that tokamak would enter into the reaction and shut it down. So you got to have an extremely strong magnetic field to keep those hydrogen nuclei tightly bound. Now, the only ones that we're actually planning on using right now are deuterium, which is naturally in the ocean, but also using tritium. Tritium is only produced in a fission reactor, and so it's not something that you can naturally get from the environment in any large amount. And so being able to do deuterium fusion, that's a long ways off. The tritium and deuterium is what we're actually trying for now. So even if the ITER works as we think it will, we're still a long way off from just using deuterium, naturally occurring elements, to power a fusion reactor. But that's the basics of it. It's the right-hand rule and keeping those protons in these cyclical orbits around the magnetic field that goes around the central inside of the tokamak, which kind of looks like a big donut, a hollow donut, maybe the inverse of a donut, something like that. So I hope that helps. Thanks for the question. I appreciate them. And keep them coming. Thanks. Bye.